All right, welcome. Today we are tackling Lab 3, Standing Waves on a String. We're going to cover everything you need to know to absolutely crush this lab, from the pre-lab quiz right through to the final calculations. So let's just jump right in.
So, have you ever really thought about how a guitar works? I mean, how can one single string produce so many different notes? Well, it all boils down to the physics of vibration. And today, you're not just going to read about it. You're actually going to be the one making and controlling these cool wave patterns.
Okay, so first things first. Before we start plugging in numbers or measuring anything, we've got to know what we're actually looking for. So, what is a standing wave anyway?
Right, so you know how a wave in the ocean travels from one place to another? Well, a standing wave is different. It looks like it's just vibrating in place, standing still. It's this really cool pattern that shows up when a wave is trapped, like on our string that's fixed at both ends. And the most important things to spot are the points that aren't moving at all, we call those nodes, and the parts that are moving like crazy, those are the antinodes.
This jump rope analogy is honestly the best way to get it. Picture this, you're swinging a jump rope with a friend. Your hands are basically the fixed ends, right? And when you get that rhythm just right, you get that one big perfect loop. That's it. That's the simplest standing wave. The big swooshing part in the middle, that's your antinode. And your hands, which are barely moving, those are the nodes. Simple as that.
Okay, so we know what to look for. Now let's dig into the physics behind it all. Pay close attention here, because this is the stuff you absolutely need to know, not just to do the lab, but to nail that pre-lab quiz.
Let's focus on that word node. It's super important. A node is simply a point where the string isn't moving at all, zero movement. And how you'll know what kind of wave you've made is by counting the number of loops, those are the antinodes, that are flapping between these still points, these nodes.
And that brings us to our first big formula. This equation right here is key. It connects the wavelength, that's lambda, to the length of the string, L, and something called the mode number, which we're calling N. And N is super easy. It's just the number of loops you see. One loop, N equals 1. Two loops, N equals 2. You get the idea. What this formula is really telling us is that you can't just have any old wavelength. Only specific ones can perfectly fit on the string.
So here's the entire point of the lab, the main mission. We're going to find the wave speed in two totally different ways and see how well they line up. The first way is the experimental velocity. We get that from stuff we can actually see and measure, like the frequency and the wavelength. The second way is the theoretical velocity. This one comes from the physical properties of the string itself, like how tight it is, that's tension, T, and how heavy it is, that's mass per unit length, mu. And the big question at the end of the day is, do we get the same answer?
Okay, quiz alert. This is huge. Seriously, write this down. The motor that's shaking the string is set to a fixed frequency. It's always going to be 120 Hertz. That value, F, is a constant. It never ever changes during the entire experiment. So burn that number into your brain, 120 Hertz. You're going to need it.
All right, enough with the theory for a second. Let's talk about the actual gear you'll be playing with, the tools of the trade, if you will.
So when you walk up to your station, this is what you'll see. You've got the motor, that's what's making the string vibrate. You've got the string itself, a pulley to make sure everything moves smoothly, a hanger with some weights to create tension, and of course, a meter stick for measuring. It's a pretty straightforward setup, but it does the job perfectly.
Okay, let's get into the nitty-gritty, the step-by-step procedure. This is where all that theory and those formulas come to life.
So here's your mission in 4 simple steps. Step 1. Measure your constants. That's the length of the string, L, and its mass per length, mu. Step 2, and this is the fun part, you'll start adding weights to create 5 different wave patterns. Step 3, for each perfect pattern you make, you'll write down how much mass it took. And finally, step 4, you'll head back to your notes, crunch the numbers, and compare those two velocities.
First thing you're going to do right out of the gate is set your length, L. Now, this is the distance from the little vibrating motor all the way to where the string first touches the pulley. The rule is, make it 60 centimeters or less. Got it? And here's the crucial part. Once you measure and set that length, you do not change it for the rest of the lab. Lock it in. It's another one of your constants.
Okay, so you're going to be adding little weights, one by one, and you'll see the strings start to dance around. But how do you know when you've hit the jackpot? How can you tell when you've got a perfect standing wave and not just some messy vibration? You're looking for a few key things.
First, the pattern should be super stable and clear, not all blurry and chaotic. Second, the loops should be as big as they can get. That's what we call maximum amplitude. And probably the most important sign, the nodes, those still points, should be razor sharp. They shouldn't be wiggling around at all. Your job is to finesse the weight until you get that perfect picture for one loop, then 2 loops, then 3, 4, and 5.
All right, so you've done the hands-on part. You've found all 5 modes and you've got your list of masses. Now what? Well, now we take that raw data and turn it into some real physics. It's time to crunch the numbers.
First up, you got to figure out mu, the mass per unit length of the string. And here's a pro tip. Please do not cut up the string on your setup. Your instructor will have a separate piece of the exact same string for you. Just take that piece, weigh it, measure its length, and then divide the mass by the length. Oh, and another thing, make sure you convert to kilograms and meters before you do the division. It'll save you a headache later. Your data table is going to look pretty much exactly like this. Just take it one row at a time. For n equals 1, first you'll calculate the wavelength using that 2L over n formula. Easy. Then take that wavelength and multiply it by our good old constant frequency. Yep, 120 Hertz, to get your experimental velocity. Then you'll take the mass you wrote down, m, figure out the tension, and use that to get the theoretical velocity. Then you just do it all over again for n equals 2, 3, 4, and 5.
And you might be asking, how do I find the tension T? Super simple. It's just the force of gravity on the hanging mass. So you take the mass, m, that you recorded for that mode, make sure it's in kilograms, and multiply it by g, which is 9.80.
And here's the grand finale, the percent difference calculation. This is where it all comes together. This formula spits out one number that tells you exactly how close your 2 velocities were. If you get a really small number, like under 5%, pat yourself on the back. It means you did an awesome job, and your results line up beautifully with the theory. Okay, last thing. Before you even start thinking about the lab report, let's put on our physicist hats for a second and think about what our results really mean. Look, your percent difference is not going to be 0. And that's not just okay, it's expected. This is real life, not a perfect textbook problem. So the big question you need to tackle in your lab report is why? What else was going on? Think about it. Could the pulley have some friction? What about air pushing against the string? Is the string perfectly flexible? These little real-world factors are your sources of error, and digging into those is what takes your report from good to great.